As you can see from the title of my talk, it is on childhood cancer. And just to give you some background on this, unfortunately kids do get cancer too. In total there are 42 new childhood cancer cases in the United States every day. So that's a classroom of children getting diagnosed with cancer. And the average age of those children is 6 years old. So it comes down to about 1 in 300 kids getting cancer by the time they're 20 years old. And actually, cancer is #1 killer of our children by disease. And in fact, it kills more children than all of the other diseases combined. Cancer is something kids in our community get as well. And we have representatives from really great organizations here, Jacob's Heart and Team G Foundation, who are touched by these diseases, and they do a lot for families who have kids with cancer. So I encourage you to talk to Lori and Kristen and Adam later and find out about their great organizations. So just to start off with some good news, cancer was a lethal diagnosis in the 50s, with virtually nobody surviving beyond a couple of months. And today we have more than 80% of children surviving for 5 years at least since diagnosis. So this is really great success. However, this is only the beginning of a success story, and much of that success is due to our progress with treating the most common type of childhood cancer called acute lymphoblastic leukemia. This slide is complicated and I'm sure people cannot see the details, but I wish I could tell you that the progress in treating acute lymphoblastic leukemia came from us discovering a magic bullet. That's unfortunately not the case. The progress in this disease came from us combining various poisons, or what we call combinational chemotherapy. So the idea is that chemotherapy kills all cells, however it kills cancer cells more so than normal cells. And so by combining these multiple chemotherapies, we are able to control these leukemias, and we have produced some cures despite the really aggressive nature of these treatments. But nevertheless, this is a great medical breakthrough. We are curing over 90% of kids with acute lymphoblastic leukemia, or ALL, today. And this paradigm of combinational chemotherapy is actually used very widely in adult cancers as well. So breast cancer patients, prostate cancer patients, lung cancer patients are all benefiting from this advances that actually came from studies in children. So childhood cancer is still devastating. We've had some progress with ALL and some diagnoses, but then there are other diagnoses such as diffuse intrinsic pontine glioma, or DIPG, that remain lethal today. And actually this fact, very few people know that Neil Armstrong's daughter actually died of DIPG, which is a rare pediatric brain tumor. And so, and that was in... Oh, yay! So that was in...
Just a couple slides. Don't let it distract you.
Right, so you're seeing here... okay, can we go to the next slide? I think we've talked about that. So, Neil Armstrong's daughter died in early 60s, and today, if a child is diagnosed with this disease today, the treatment is exactly the same as what his daughter received in 1962, and the only treatment option is palliative radiation to the brain, which does not really save the child, so it's 0% survival. It's a very devastating disease. Can I get the next slide? What about other diagnoses? So I would like to walk you through the journey of a typical, what we call high-risk patient. So high-risk patient means child that does not respond, so would not respond to this combinational chemotherapy that we've talked about. So can you please click? Yeah, just show the whole thing. I think the idea here is that these children go through a lot of clinical trials with varying successes. Some of these clinical trials produce remissions that then followed by relapse. And then in this particular case, the patient eventually passed away. So what I wanted to show with this story is that we are making progress. We are opening new clinical trials, and they work. Sometimes they show success. And this also illustrates the determination of families to really travel the country to access these clinical trials and try everything they can for their child. Next slide, please. But what's the most striking thing to me from this example is that this patient that I just showed is actually considered a long-term survivor, because this patient survived 7 years since diagnosis, so he would be in the yellow bar, so in what we call success. Because the measure of success is defined as a 5-year survival is what we use for adults. It's completely inappropriate for children, and you would agree with me, this is absolutely not good enough for our kids. So next slide. If you look at long-term survival, so this is 30-year survival, only 20% of these kids will lead a completely normal life. About a third of them will die 30 years from diagnosis, and then many will suffer significant side effects due to the fact that we're using these really aggressive treatments like combinational chemotherapy to treat them. So we must do better than that. We must use smarter approaches than just brute force therapy and throwing everything we have at these kids. Next slide. And the question is, we all heard this word genomics. So can genomics point to new treatments, new, more targeted therapies, so that we are smarter about how we treat cancer, so that we understand what the cancer cells really are and just treat them while sparing normal cells? Next slide. So this is some background on what genomics is. Genomics refers, or our genome refers to the DNA that we have in our cells. So every cell in our body has DNA, which basically can be thought of as a set of instructions for how the cell and the body functions. And so that's called the genome. Collectively, all of the DNA is called the genome. And you can think of it as a book composed of letters. So as we go through life, these letters can change or mutate as a result of environmental exposures, radiation, chemicals, smoking, and so on, but also as a result of random errors, just by random chance, this DNA can mutate. And so these mutations can be thought of as spelling mistakes in our genomes, and eventually these spelling mistakes lead to cancer. So normally cancer cells would have not one, but several of these spelling mistakes that then cause cells to grow uncontrollably. Next slide. So we have known about this for quite some time, but only now in the last decade it is actually affordable for us. We have the technology, and it's affordable for us to be able to read cancer genomes, so to be able to read the DNA and find those spelling mistakes. So this is really a paradigm shift in how we understand cancer, because now we can actually read the DNA and see what those spelling mistakes are. And just to give you an example of the cost, so now it costs less than $5,000 to read one child's genome, compared to about $200,000 for a bone marrow transplant that many of these children go through. So this has been very exciting, and in response to this technological breakthrough, several initiatives have been set up around this country and abroad to read the genomes of childhood cancer cells. One initiative is Target, so this is the US government National Cancer Institute initiative. St. Jude has an initiative called Pediatric Cancer Genome Project. The MAGIC initiative is run from Toronto Children's Hospital of Sick Children. So all of these initiatives have used DNA sequencing, or the technology that allows us to read cancer DNA to understand what those cancers are. And the goal, of course, is to find those spelling mistakes and develop therapies that would be specific to cancer cells while sparing normal cells in that child. Next slide. So while this has been really exciting in adults, because of course the same is true for adults and we can read the genomes of adult cells as well, however, with children, we have been a little bit disappointed with these genomic studies because it turned out that childhood cancer cells have much fewer spelling mistakes than adult cancer cells. And perhaps that makes sense because these children are so young, so they have not been exposed to a lot of toxins as adults would be. And so there's much fewer mutations. Also what we found is that mutations are rare, so every tumor is really different from the next tumor. And so if that's the case, it is very, very hard to develop therapies because every mutation is really unique, so you need to develop as many drugs as there are patients. So hard to develop drugs and hard to design clinical trials. Next slide. Nonetheless, genomics has been very helpful for treating and understanding childhood cancers. So one example here, this is a patient of our collaborator, Leonard Sander, Children's Hospital of Orange County. So this girl was diagnosed with Ewing sarcoma, and she went through a lot of aggressive treatments that are listed there. So it was 4 years of treatment, multiple PET scans, MRIs, 2 autologous stem cell transplants, 2 clinical trials. None of that worked for her. And it was estimated that the cost of care was close to $1 million. And then eventually the genome of her tumor was sequenced, and it was revealed that she had a particular spelling mistake listed there. But the point of that was that she was treated for the wrong disease. So had we known her genome sequence in the beginning, she would not have had to go through some of these therapies. But unfortunately, in that case, it was too late. Next slide. So, as I mentioned, genomic analysis has helped us refine diagnosis or understand or arrive at the correct diagnosis for some patients. It is also can suggest new treatment options. So this is an example of our own work that I did when I was a graduate student in Vancouver. So in that work, we read genomes of a cancer called neuroblastoma, and so we studied 240 patients, and what we found that in 22 of those 240 patients there was a spelling mistake or a mutation in a gene called ALK. So that's about 10% of neuroblastoma patients. It so happened that ALK is also mutated in a subset of adult lung cancer patients. And so what we learned from this genomic analysis is that there are similarities between childhood cancers and adult cancers, even though in this case the ALK mutation is pretty rare by itself in neuroblastoma. Next slide. So it turns out that company Pfizer had a drug, crizotinib, that was going through trials for adult cancer patients with a particular ALK mutation. And because of this observation, Pfizer opened a clinical trial of crizotinib, which is an ALK inhibitor in neuroblastoma, and it took only 12 months from the discovery of ALK mutation in neuroblastoma to the opening of this new clinical trial because the compound was already in the clinic for adults. This is Anna. She was the first patient, the first neuroblastoma patient on this clinical trial of crizotinib. And so before she tried this drug, nothing was working for her, and she responded to this drug. So this is pretty significant, and what we have learned there is that there are these important similarities, even though childhood cancer mutations are rare, but sometimes there are similarities that can lead to these new treatment options. So you're probably sitting there and wondering, well, why don't we compare all of childhood cancer genomes to all of adult cancer genomes and look for such similarities, since we know that there are many more drugs for adults? Next slide. Unfortunately, that's not very easy to do. While generation of sequencing data or reading of these genomes is affordable, and a lot of people are doing that, a lot of hospitals, a lot of laboratories are doing that, the data that's being generated are really siloed. These are really big data sets, and there are regulatory issues with sharing genetic data. So the data are siloed, and it's very hard for us to do this comparison because we're unable to access all of these data. And so this is what we're in the business of doing at UC Santa Cruz, is creating a platform and creating ways to consolidate all of these genomic data together so that we can make discoveries like the crizotinib repositioning from lung cancer to neuroblastoma. So David Hausler, the director of our institute, co-founded this coalition that's called Global Alliance for Genomic and Health, and this now has over 300 member organizations in 37 different countries. And so all of these organizations are committed to sharing genomic data, and they're developing standards and also regulatory framework for how this sharing can take place. And so building on that, we started what we call the Treehouse Childhood Cancer Project that specifically focuses on sharing data from pediatric cancers. And so we have partnered with a number of children's hospitals and research groups that are generating genomic data. And so they are all committed to sharing the data with us. And so we are creating a platform for them to do this. And also what's important is consolidating these data with data from adult cancers. Because adult cancers is where the drug development is taking place, and that's where all the drugs are. So we're hoping by doing this we can identify situations where an adult drug can be useful for some children. And so for the next little bit, I'm going to talk to you about how exactly we do it. I have been saying we will consolidate the data, but how are we going to do it? Next slide. So George Stewart, who's a professor at UC Santa Cruz, developed, so his group developed this tool that we call Tumor Map. And this can be thought of a Google map of all of cancer genomes. And Julia Newton here in the audience, she's a graduate student working very closely on this project, and this is her baby. So if you are interested in details of how that works, Julia can talk to you. So essentially what you see here, so you see a lot of different dots. Each dot here represents a cancer patient or represents a cancer patient's genome. And then the dots are laid out here to indicate how similar any two tumors are to each other. And then they're color-coded by the diagnosis that these patients have. And so you can see, for example, that breast cancers there in blue are all clustering together, and they're clustering away from ovarian cancers, so showing that breast cancer genomes are more similar to each other than they are to ovarian genomes. But you also see that there are some wrong colors infiltrating these blobs. And so that represents patients that perhaps were diagnosed with a bladder cancer, but their tumor at the level of the DNA is actually more similar to another type of cancer. And that's pretty significant. Next slide. And so I'm going to show you what it means for childhood cancer patients. And I'm going to illustrate with a concrete example that we have. So this we call him patient 1. This patient was treated by our collaborators at British Columbia Children's Hospital in Vancouver, British Columbia. So this patient had a rare sarcoma, dural-based sarcoma, 8-year-old boy, underwent standard treatment, which is aggressive chemotherapy and radiation. Unfortunately, 2 years later, the cancer returned in his lungs. And because this was a rare sarcoma at that point, there was no treatment options for this child. So it was either hospice or this clinical trial, and the parents chose the clinical trial. And so in this clinical trial, the genome from this tumor was sequenced or read to try to understand what the tumor is and see if that can be used. And so this particular spelling mistake or mutation was found, EWSR1 ATF1. So what it means that two genes are now abnormally fused together into one gene. And so while this is interesting from the biological point of view, and we know why perhaps he has this cancer, but unfortunately today there is no drug that can fix that. And so for this particular child, there is no options. So now what? Next slide. So our collaborators shared these data with us, and we were able to use the tumor map tool that I presented previously to look at this patient's tumor in the context of all the other cancers. And Julia made this map actually. So you can see that patient 1 here is shown with a green arrow and green dot. And so I mentioned that this was a sarcoma, and we had some other sarcomas that we had access to in our database. They were adult sarcomas. And so you might expect, or we might have expected, that this sarcoma would cluster with the sarcomas, but in fact it did not. In fact, in this tumor map, it turned out that it was looking like his cancer was more similar to another type of cancer called neuroblastoma. You can see it's right in the middle of the blob of neuroblastoma patients in gray. Next slide. So I just mentioned neuroblastoma, and I mentioned that in neuroblastoma there is this subtype of neuroblastomas that have ALK mutation, and those ALK mutated patients respond to this drug crizotinib that's approved in lung cancer, and now it is in clinical trials for neuroblastoma. And so just to show you here on the y-axis, or on the vertical axis, we have the levels of this ALK gene. So in addition to mutations that I showed you that are spelling mistakes or change in the letter, cancer cells can also have an abnormality where the amount of a gene product, or how much of some gene is present or is expressed, is abnormal. And so in this case, we're looking at the levels of ALK gene in lung cancer patients that are known to respond to this crizotinib, and in blue, and then in black we have neuroblastoma patients that are also known to respond to crizotinib, and then we see in green patient 1. So you can see from this graph that patient 1, or the green bar, looks very similar to the blue and the black bar, but not to the purple bar, which is other sarcoma patients. Next slide. So when we presented these results to the doctors, to the treating physician for this patient, he decided to actually try crizotinib for this patient. Next slide. So unfortunately, that was not the miracle we were hoping for. He had a partial response, but we did provide this family new hope, and the mother of this patient was very happy that something was being tried. But, so next slide. We did not stop there. We actually looked deeper at what might be causing the cancer in this patient. So on the left here, I have a cancer cell that's in this patient, so patient 1, cancer cell in green. And so just to show you, so ALK was one thing, so whatever is in red is not normal. So that means it's too much of that in patient 1. And so it turned out that while ALK was abnormal, so there was too much ALK, there was also too much JAK, which is another gene that's downstream of ALK, and so resulting in uncontrolled cell growth. But in addition to ALK, there was also abnormalities in these other things, FGFR1, IL6R, and so just without too many details, it turns out that there are multiple things that are driving uncontrolled cell growth in this patient. So if you just click once. So if you inhibit ALK, there are these two other things that are feeding into JAK and feeding into uncontrolled cell growth. So kind of explaining why this patient did not respond to ALK inhibitor very well. So click again. So instead of inhibiting ALK, click again. What if you inhibit JAK? And so if you inhibit JAK, you might suspect, because JAK is downstream, that you might be able to maybe stop this uncontrolled cell growth. And click again. And even though ALK is there, is too much ALK, but there is no JAK now, and so maybe this is a better strategy. Next slide. So it turned out that there is a JAK inhibitor that's available for adult patients again. It's called ruxolitinib, and it's also in clinical trial for pediatric patients. So that was tried next. And so in August, we were very happy at the Genomics Institute when we learned that the patient had a turnaround on ruxolitinib. So he responded and he felt very good. Click again. So I don't want to oversell this idea. Unfortunately, we just learned that in January, just this month, that the cancer started growing again. Just showing to you, this is a completely new concept, and this is just the beginning, and we need to do much more work than that. And we are doing that work, and we're not stopping. And just bringing me to the California Kids Cancer Comparison, I'm very happy to share with you that we actually have a new initiative, a State of California initiative that was launched by Governor Brown's office. And this project, the California Kids Cancer Comparison Project, was chosen as one of the 2 official demonstration projects for the California Initiative to Advance Precision Medicine. So we're very excited to be able to apply this approach that I just described for patient 1 to 150 California children that are out of treatment options for their cancer today. So we're very excited, but we have bigger dreams than that. We want every child with cancer to have their genome read and sequenced and analyzed early on, not at the stage when they failed all treatments, but actually early on, so that we can understand their disease and then learn from the genome. And we would like every child to have access to therapies based on their genomic data. And we would like to see companies, advocacy groups, and researchers and clinicians working together, because this is really a community problem. And we have to come together as a community to fix this. So, thank you very much. I'd like to thank our partners that conduct clinical trials for us, the UCSF, Children's Hospital, Hyundai Cancer Institute, Stanford, BC Children's Hospital, our advocacy partners, some of whom are here, and thank you so much for coming and for supporting us. And I would also like to thank patients and families. So those dots on the tumor map, if we didn't have those dots, so if those patients did not donate their data to research or did not participate in those research studies, we would never spot these similarities. So it is very important to participate in research, and we would like to thank those patients. Thank you. Questions?
So what is stopping every child's diagnosis with their sequencing? Can't be money, it's not expensive.
That's a good question.
Can you repeat the question?
So the question is, what's stopping us from having every child's genome sequenced at diagnosis? It can be money because it's not so expensive. So another issue other than money, even though it's not expensive, but it's still, we still need money to do that. But another issue is sample availability. So we have to educate pathologists and surgeons to preserve the sample in a way that we can use it for sequencing, which is different from what's done in routine care. So there is some limitation with availability of the tissue from these tumors. And then also, I think awareness, we have to spread the word that this is useful, that this is going to be useful. Because we do have standard of care, and we are, like I mentioned, for leukemia, we are curing 90% of patients without combinational chemotherapy. So it is very hard for us not to do it when we know it works, even though it's not ideal, but it works. And to do something that's experimental. So I think we have to do more work proving that this is the right thing to do, but I think we'll get there.
Is it not patient confidentiality that also hinders the sharing of?
So in terms of data sharing, yes, there is definitely issues, there's definitely regulatory issues. And what's interesting actually is when I ask patients, and I don't know, maybe parents who are present here might disagree, but when I ask parents, usually parents are very willing to share their data. It's our perception of what they want that's different. It's the IRB and the lawyers that we have to convince.
What keeps this information from being taken by some third party who it could eventually end up on the internet or with insurance companies is the big thing to be afraid of. We may not have the tools today to map a genome to a particular person, but 10 years down the road that may be common.
I mean, we have tools today to actually map the genome back to a person, but my favorite lawyer, Barbara Evans, gave this great analogy. one of the few, not one, but gave this analogy. So we know that driving can kill people, right? There is so many people dying in car accidents, but we also know that we must drive to save lives. And so we don't stop driving because people get killed from driving, but what we do is we regulate it. So we have speed, so I think we just have to do it smartly and regulate it and do it in a secure way, like you mentioned, to avoid or minimize those risks.
In your experience, what seems to be the barrier between having other companies or other countries share their data? Because it seems like you guys have been working this for a long time and these countries aren't as helpful. But like, why is that not being processed that long?
Right, so there is actually a lot of capital in the data. There is a lot of discoveries to be made from having access to a lot of data. And so we see that some companies are doing that. They're holding on to the data while they're analyzing the data to make some discovery, that then they can patent and so on. So there is that. And I think in an academic setting that also exists, because in academia we're judged by how we publish, by how many publications and what journals. And so many people are afraid to share the data because they feel they wouldn't get the credit in publication that they need to get the next grant. And so I think part of that we have to change how we judge somebody to be successful. Is it really just the number of publications? But could we include some sharing index? So our colleague Ted Goldstein has this thing he called sharing index. Should we judge scientists by how they share? And if you share, maybe that's good and you should be rewarded. In addition to how well you publish. In the back?
Have you sequenced the genome of a tumor multiple times over like a treatment? Like how you said you sequenced patient 1 and you figured out that JAK was something to inhibit, and then in January it started coming back again. Did you sequence it again to see if the tumor somehow mutated a detour around that?
And that's a great question. So the question is, I was talking about sequencing tumor only at one point, at diagnosis or at first relapse, but actually, as this gentleman pointed out, tumors change, they evolve. So the mutations that we have at diagnosis may not be the same mutations, or we know that they're not going to be exactly the same mutations that we see in relapse. And so ideally, we would like to sequence the tumor at relapse to understand what it is now. And especially since we are treating these cancers with chemotherapies that are causing mutations themselves to the tumor. So we would like to absolutely do that. That has been done a little bit in the research setting, but I don't think we do enough of that.
Is your database also collecting gene expression data to incorporate in?
Absolutely, and actually the ALK, patient 1 example, so that ALK and JAK. So the question is are we collecting expression data? So expression data means just the amount of these gene products, so not just the sequence, but also how much of each gene we have. And we're absolutely collecting that. And for patient 1, that was actually the data that made the difference. So it was abnormal amounts of JAK and ALK that we acted on.
Are you able to uncover any of the non-coding regulatory sequences that might be involved in it?
So the question was, are we able to uncover regulatory sequences? So regulatory sequences would be changes in the DNA, so spelling mistakes in the DNA that affect the amount of gene product. So not really changing the gene itself, but changing the amount. And right now, I think absolutely we should look there, but it's not, again, being done enough, because right now we're going for the low-hanging fruit of coding changes, but I think definitely we should be looking there as well.
I have a question. Just when you have the sign up there for the 5K and the 10K, I'm wondering if you could tell us about that, and also just make some suggestions about what people can do.
Thank you, and I swear this was not set up. So we also have flyers, and our other advocacy partner, Unravel Pediatric Cancer, has committed to raising money for this project as part of Team Glitter. So some of you may know about this She's Beautiful race that takes place in Santa Cruz every year in March. And so as part of that, There is Team Glitter, which is a group of runners that are dedicated to raising money specifically for Unravel, who is going to give us some of the proceeds from that. So if you're interested in running or raising money or volunteering at the race, we are looking for volunteers as well. If you're not a runner or if you're not comfortable running with a lot of women. So we have volunteer opportunities, and I have a flyer, and please come talk to me in terms of what else you can do. Like I mentioned, Lori and Kristen here, they run advocacy groups, Team G Foundation and Jacob's Heart, and they have volunteer opportunities as well, I'm sure. So if you'd like to contribute in that way, please come talk to them. And spread the word about data sharing. That's my thing. I think we have to get over our fear of sharing data, and yes, we must do it responsibly, but that should not stop us from doing it.
Could you learn a little bit how you got those dots on a tumor map? I find this a really revolutionary tool, and I think I'd like to know how that's done a little bit.
And thank you for that question. And so that just speaks to the point that those dots are patients who have participated in research studies. And so the big adult research study that was done called the Cancer Genome Atlas, and then the pediatric study that's called Target, or Therapeutically Actionable Research to Generate Effective Treatments, is a long name. But those studies had research participants who gave their sample to be analyzed, and they actually agreed for their data to be publicly available and to be used in this way. And so thanks to those people, we were able to see that patient 1 is similar to neuroblastoma. So this just shows you that by sharing data, these people actually saved this patient's life, even though they don't know it and we don't know who they are.
So is that number constantly increasing with your work, the 8,618 patients?
Absolutely. So in this...
Wait, the question.
Oh, so the question is, I'm showing that there were 34 different cancers and over 8,000 patients in this map. And yes, that number is increasing. And I think as that number increases, right now this was a lucky coincidence that we were able to show something that was clinically significant. But I think as that number increases, those anecdotes will not be a coincidence, and we will in more cases find something useful as we have more data in the tumor map. Well, I'll be around.
Thank you so much. That was great. And I'm glad that we got the PowerPoint to work so that we can have these awesome. I'm sure that if we think about how much work went into this image, it's pretty amazing. Yeah, so great. Hopefully you guys can stick around a little bit in case there are any questions. Thank you again so much for coming out tonight. Thank you for being patient. Hopefully next month we won't have these problems. Next month we will be having Michael Stone, who will be similar, more in chemistry, biochemistry, and thinking about telomeres and telomerase. So I don't have the title of his talk offhand, but we will be here again on February 25th or 24th, I believe. So please come out if you have the time. It's again the fourth Wednesday of every month. I'm Monica. If you have any questions, I'll be around a little bit as well. Or if you have suggestions for speakers you'd like to hear come. And again, I'm from Women in Science and Engineering at UCSC. So thank you so much for coming out tonight. Thank you so much, Olena, and have a great night. Hope to see you again.
Lori, nice to meet you. So what do you want to do?
And if things work out, I'm gonna walk back. I just stand by the right here. Okay. Stand by the fire. Yeah. I'll let you know.
So that's like the highest
And